Hello student, welcome to the lecture on demand forecasting, and after this lecture, we will be able to learn the following objectives. Comprehend the purpose of forecasting demand, give details of time series and seasonal indices, talk about the method of simple average. Purpose of forecasting demand. Demand forecasting is essential for a firm because it must plan its output to meet the forecasted demand according to the quantities demanded and the time at which these are demanded. The purpose of demand forecasting differs according to the types of forecasting. The purpose of the short-term forecasting. It is difficult to define short run for a firm because its duration may differ according to the nature of the commodity. The purpose of long-term forecasting. The concept of demand forecasting is more relevant to the long run than the short run. It is comparatively easy to forecast the immediate future than to forecast the distant future. Steps involved in forecasting. There are usually 5 basic steps in any forecasting task. Step 1. Problem definition. Often this is the most difficult part of forecasting. Defining the problem carefully requires an understanding of how the forecast will be used, who requires the forecast, and how the forecasting function fits within the organization requiring the forecasts. Step 2. Gathering information. There are always at least 2 kinds of information required: statistical data and the accumulated expertise of the people who collect the data and use the forecasts. Step 3. Preliminary exploratory analysis. Always start by graphing the data. Step 4. Choosing and fitting models. Which model to use depends on the availability of historical data, the strength of relationships between the forecast variable and any explanatory variables, and the way the forecasts are to be used. Step 5. Using and evaluating a forecasting model. Once a model has been selected and its parameters estimated, the model is to be used to make forecasts. Extrapolation techniques of demand forecasting. For controlling inventory, numerous techniques of demand forecasting. Time series analysis. The basic elements of this pattern are constant value, trend, seasonal variations, cyclical variations, random variations, turning points. Qualitative. Qualitative forecasting consists of gathering opinions from a variety of people, then applying their own judgment. This technique is best used when there is not sufficient historical data. Causal. This is the application of leading indicators to create a forecast. It assumes demand is strongly related to these indicators. Mortgage rates, for instance, strongly affect the purchase of new homes. Simulation. Simulation forecasting combines the causal and time series methods. It is often used when creating what-if scenarios. Time series and seasonal indices. Economic time series data can be broken down into 4 compartments. Secular trend, the smooth long-term direction of time series. Cyclical variation, significant fluctuations above and below the secular trend that occur over an extended period of time series. Seasonal variation, fluctuations in data that regularly occur at about the same time each year. Irregular variation, variations that are neither cyclical nor seasonal. Episodic variations, identified with random occurring events. Residual variations, small random fluctuations that are unpredictable and associated with neither specific events nor cyclical variations.
during the year. So in other words, so you might even chop off a little bit more extra for the fact that it happens to be the first quarter of the year is not the summer, but whatever the first quarter of the year, let's say for that particular business, is traditionally and historically very much below the average throughout the rest of the year. So basically, our job is to figure out what impact does the cycle have, what impact does the season have. Now, the I can't be figured out. By definition, it's totally unpredictable. The I is like what? What symbol do we have for the I in other chapters? You got to answer quickly because we only have 20 minutes to cover an important topic. What symbol do we have for the I in other chapters? And the answer, to give myself a point, is the epsilon. The epsilon was like the amount that's totally, the deviation from the straight line was totally unpredictable. And also, but that was in chapter 13 and 14. What about in chapter 11? What symbol do we have for the error in chapter 11? And the answer is, to give myself another point, the sigma squared. The amount of, remember, people are different, people are just randomly different. That sigma squared of experimental error, for those of you who might still remember this, the sigma squared of experiment. So every chapter really has built into it in statistics a recognition that there's going to be a certain amount of randomness that has to be taken into account mathematically. Now, I told you that our job is to calculate these four things. Now, this thing you can't calculate. We'll deal with it by averaging things out so that the pluses and minuses will cancel out. The T we're going to calculate by the B0 and the B1. We'll do that in a couple of minutes. The C we're going to deal with by simply saying, let's make believe there's no cycle. In other words, let's make believe this particular data is there's no cycle here. It's just a straight line and a season. Why? Because just mathematically, I want to show you the thing quickly. And once you do this on a real life on a computer program, you would tell the computer to take into account all three of them. But for our purposes right now, we're simply going to eliminate the possibility that the data has a cycle. And finally, how do you calculate the season? Well, the season by itself is not a single number. Basically, it's going to be four separate numbers called S1, S2, S3, and S4. It's basically what impact does being in the first quarter of the year have on your data? And the answer is, say, traditionally, in the first quarter of the year, the data is down by 5%. Traditionally, during the second quarter of the year, the data is pretty much the same as the average throughout the year. S3 may be up by 5%. S4 might be, flat. The point is each one of these might be a separate little number indicating that if you know you're in the first quarter, this is now the first quarter of the year, so you would impact this particular forecast by the amount that the S1 tells you you're supposed to make the adjustment by. Now, if this sounds complicated, it's not. In reality, it's really a bunch of straightforward, simple multiplying and dividing steps that we're going to implement right now. Okay, so the first step is to cast. The first step is to show you some data. So what we got to do right now is fill in the following chart. So the next 10 minutes, we're going to fill in the following chart, and hopefully the last 5 minutes will make the actual forecast. But again, 90% of the chart is simply calculating the B0 and the B1, which everybody hopefully knows how to do already. Okay, so here's the data. So you're given the data in the following format. You're given the Y data. You're told what year it's in. You're told what quarter it's in. And let me just give you some real life data. Stands for is not relevant because I'm only using part of the data. But let's say it stands for the amount of building private residential construction. Okay. So it says 2008. Actually started this in 1998. Oh my God, 1988. Okay, 2008, 2009, better yet, 2008. Now, quarter one had a value of 10.2. Quarter two had a value of 12.4. Quarter three had a value of 14.8, and quarter four for that year had a value of 15.0. That's 1 year. You can't make predictions based on 1 year. You need like 5 or 10 of 20 years, but we're going to do it with 2 years. 2009, the first quarter was 11.2. Quarter two was 14.3. Quarter three was 18.4. And quarter four was 18.0. And again, you really can't do this And practically, it's such a small amount of data, but we'll try to see what we get. Okay. Now, can somebody suggest what I'm going to ask you to do next? What? You said plot it? Yeah, it was always good. If I can teach you one thing in life, plot the data, you're going to be way ahead of the game. So let's plot it quickly. Now, we can take 2009, quarter 1, 2, 3, 4. This is the Y value. It goes somewhere between 10 and 18. So we got to go 10, 11, 12, 13, 14, 15, 16, 17, 18. What'd you say? 2008, thank you, 2008. And this 10.2, do it quickly because, again, we only have a few minutes, 12.4, 14.8, 15.0. Then we're going to go 11.2, for them would be 2009, 1, 2, 3, 4, 2009. 2009 was 11.2. Then 14.3. Then 18.4. And 18.0. Now, would you connect it like this? Or would you connect it by a straight line? The answer is at this point, well, if the data had a nice pattern, if the data followed one of the patterns I'm trying to teach you, I would connect it like that. But really, we just want to create basically the straight line through the data. And the straight line was something like this. Okay, so again, I wouldn't argue that there's a clear pattern here because there's only 8 dots and the numbers are pretty variable. But what the data is supposed to show us, this formula works great when the data has, again, pretty much a straight line data with some meandering up and down according to the quarters of the year. And if there's cyclical data, of course, you'd have to do a slightly different approach, but it would be very similar to what we're doing here. Next, so the basic approach to this problem is we're going to calculate the t. And we're going to try to get. Let me just tell you sort of what we were going with this. We're going to calculate the trend. We're going to say where will be the prediction for each point. What's the prediction here? The prediction here? The prediction here? Prediction here? We're going to make a prediction for each one of these values by the same method we used in chapter 13 many times over. Then we're going to figure out how far apart is the prediction from the actual. Now, the difference between the prediction and the actual can be explained by what? The amount that the data deviates, the straight line deviates from the actual data can be explained by what? Well, the 3 factors that influence the data are the trend, the season, and the irregular. So the fact that anything that deviates from the trend has to be attributed to the season and the irregular. So we're trying to isolate, remember, our goal is to isolate the season. That's our goal of this whole thing. So then we can make adjustments to get the best kind of forecast. So we're going to calculate the t by the method of chapter 13, and then we're going to calculate y divided by t is how much? Well, this we got rid of already. It's the s and the I. But we really want to focus on the s. How do you get rid of the I? The answer is, again, you'll see this in a couple of minutes. We're going to average everything by averaging the I, which is sometimes above the line, sometimes below. It's totally random. By averaging stuff, you're going to get rid of the I. You're left with a pure measure of s. And then we can basically make an adjustment. So that's the sort of the game plan for this whole thing. So where are we up to? So now the next step is to figure out the B0 and the B1 that's going to be useful for calculating the trend, and then once we get that number, we'll divide it into the Y to continue the next couple of steps. Now, what is the B0 in this case? Can somebody make a quick guess at what the B0 is going to be? What? It's going to be around 10. It seems to be going, so in fact the B0 when we do should come out to around 10. What's the slope going to be? Can you make a guess there? Well, let's see. You went from 1 to 8. We went 8, the X changed by 8 points. And how much did the Y change for during that period of time? Well, we went from about 10 to 18, roughly from 10 to 18, give or take a little bit. So it went from about 8, and it went around 7 or 8 over here. So what's going to be the slope? Probably pretty close to 1, all right? So the slope, before I make a fool of myself, let me make sure that's the answer. The answer I know for the B0 definitely is 10. Very next thing to do, if you want to tell me before I jump in and grab the point. What's the very next, we want to figure out the B0 and the B1. What's the very next thing you got to do? Yes? What? No, we can't interpret anything until after. We're not going to get into, there's very little verbal questions in this chapter, at least online in class. In chapter 13 and 14, that was part of the test, the very next interpret. But first, before you interpret something, you got to calculate it. So what's the next thing you got to do to calculate the B0 and the B1? Before we plug it into the formula, is what? What?
The first step is to calculate the yearly averages. So here we have some data, and for this year, 2003, in the first quarter we had 72, then 64, then 63, then 75. So my first step is to find out for 2003 what was the average. So how do I find the average, the mean? I add everything up and divide by how many I have. So I'm going to do 72 plus 64 plus 63 plus 75 divided by 4, because there are 4 of them. And I get 68.5. So that is the average for this year, 2003. Now what I'm going to do is work out this sales figure as a proportion of the yearly average. So I'm going to say 72 divided by 68.5. Now because 72 is greater than 68.5, this number here, these sales in quarter 1 were better than average. So my number is going to be 1 point something. So 72 divided by 68.5 gives me 1.051. So 1.051 is this yearly proportion. It's the proportion of 72 divided by 68.5. Now I'm going to do that going along for these other results. So 64 divided by 68.5, which is 0.934. And because 64 is less than 68.5, I was expecting 0 point something. Now 63 divided by 68.5 gives me 0.920. And 75 divided by 68.5, 1.095. Now if I just had 1 year's worth of data, if I just had 2003 and I didn't have this stuff down here, I could stop here because these numbers would now be my seasonal indices. This is a seasonal index for quarter 1 in 2003. This is a seasonal index for quarter 2 in 2003. However, I in fact have been given a couple more years here. I've got 2004 and 5 as well. So I'm going to need to factor these extra years into my calculation of an overall seasonal indice for quarter 1. So what I'm going to do is the same step for 2004 and work out these yearly proportions. So the first step is to find a yearly average that I can divide everything by. So I'm going to say 75 plus 66 plus 64 plus 89 divided by 4 because that's how many there are, and I get 73.5. So that's the yearly average for 2004. Now let's figure out some proportions, some yearly proportions for these 2004 figures. So 75 divided by 73.5 and 66 divided by 73.5 and 64 divided by 73.5 and 89 divided by 73.5 gives me. So filling those in, 1.020, now I have yearly proportions for 2004. Let's do the same thing for 2005. So the first step is to work out the average for that year. So 76 plus 68 plus 67 plus 95. Add them all up and divide by how many there are, which is 4, and I get 76.5. So that's the yearly average. Now, to determine these yearly proportions, I want to divide the data, the actual piece of information, by that yearly average. So 76 divided by 76.5, 68 divided by 76.5, 67 divided by 76.5, and 95 divided by 76.5. And I can tell that this one will be slightly less than 1 because 76 is just less than 76.5. This will be less than 1 because 68 is less than. This will be less than 1. And this will be 1 point something because this proportion here, 95, is greater than 76.5. Those are the figures I get, so I'll fill those in here for my yearly proportions. And now that I have yearly proportions for all 3 of the years of data that I have, I can work out an overall seasonal index for each of these quarters. Now, to find the seasonal index, I average these 3 yearly proportions. So Finding the average, 1.051 plus 1.020 plus 0.993. Add them up and divide by how many there are, which is 3. 1.021. So that is the seasonal index for quarter 1. Now for quarter 2, average these three numbers. Add them up and divide by how many there are. 0.934 plus 0.898 plus 0.888, all divided by 3, gives me 0.907. So that's the seasonal index for quarter 2. What about quarter 3? And finally, for this last quarter, we have 1.183. A handy rule to know is that the seasonal indices, the seasonal index numbers, will always add up to the number of time periods you have. So if it's quarters, and therefore there are 4 of them in a year, your seasonal indices will all add up to 4. If it's months and there are 12 of them, then your seasonal indices will all add up to 12. If it's days of the week and there are 7 time periods, your seasonal indices will add up to 7, and so on. So let's just double check these. We have 1.021 plus 0.907 plus 0.889 plus 1.183. What do you know? If you put that on your calculator, it adds up to exactly 4. Ta-da! Once you know what the seasonal index numbers are, whether because you've worked it out like this or because you've been given them at the start of the question, you can then deseasonalize this data. And what deseasonalizing does is it smooths it out. It takes away some of the seasonal fluctuations that occur. And the way you do that is using this formula. The deseasonalized value equals the actual value divided by the seasonal index. So for this 72 figure here, we want to do the actual 72 divided by its seasonal index, which is 0.021. So I'm going to say 72 divided by 1.021, which is 71 when I round that to the nearest whole number. For this 2004 quarter 1 figure of 75, I'm going to say 75 divided by its seasonal index, which is 1.021, and I get 73. For this last one, 76 divided by 1.021, I get 74, rounding it to the next whole number. Over here, my 64 becomes 64 divided by 0.907, 71. For this 66 divided by 0.907, I will get 73. And the 68 divided by 0.907 becomes 75. Deseasonalizing these last few, I'll have 63 divided by 0.889, 64 divided by 0.889, and 67 divided by 0.889. And then over here, 75 divided by 1.183, 89 divided by 1.183, and 95 divided by 1.183. And there's my deseasonalized data. When we plot those two sets of time series data on the same axis like this, you can see what deseasonalizing is doing for us. This is the actual data here in the red, and it's got some really big fluctuations, some high peaks and troughs because it's quite seasonal data. And this blue line is much flatter, it's much straighter. We've taken out some of that crazy fluctuation going on so that we can see what's really happening with these sales figures. And what I can see is that over time it is increasing slightly. It's got a slight positive trend, which is good. You want sales to go up. But the other thing I notice is that this quarter 4, this first quarter 4, so this was quarter 1, 2, 3, 4 of 2003, and then we had 1, 2, 3, 4 of 2004, and then we had 1, 2, 3, 4 of 2005. So this point here at x equals 4 corresponds to the fourth quarter in 2003. And deseasonalized, it was actually very low according to the overall trend. So this point here, it looks like their sales were up around about that time period. But because that's the end of the year, that's maybe Christmas sales, and Christmas sales are normally up here somewhere. So this year they actually had quite low sales deseasonalized. See that? So that's the kind of stuff that deseasonalizing the data can tell us. You can put trend lines, regression lines, onto time series data in the same way you can with any of those other scatter plots that we looked at earlier in the core chapter. And the three ways of doing that were by eye, which means looking at it and just plonking a line on, using the 3 median method for regression, and using the least squares method. So if you're asked to fit a trend line to a time series plot, pay attention to which method they've asked you to use, and then just draw your line on as though it were any other kind of scatter plot. So if they ask you to do least squares, you put the data into your calculator and you say lin reg a plus b x. If they've asked you to do 3 median, you split it into 3 groups and then you find the median horizontally and vertically in each section. Use the far left and the far right to get the gradient, and then you slide a third of the way towards the middle point. And if they ask you to do by eye, you just have a look at your dots and you kind of go, well, hey, and you put a line on wherever you think it kind of works. So, say your time series question now asks you to determine the equation of the least squares trend line for the deseasonalized data, and hence calculate the deseasonalized sales prediction for the first quarter of 2006. Now this is what our deseasonalized data looked like. So what we're going to do is work out a least squares trend line for this deseasonalized data as opposed to the original actual data. So I'm going to put this into my calculator in the lists, and I'm going to use this first point here as x equals 1. So 2003 quarter 1 is x equals 1. So I'll have 173, 271, 371, 463, 573, 673, and so on, going down the line. Once you've entered that into your calculator, you ask your calculator for a least squares regression line. And you get y equals 0.78x plus 67.68. Now we can use this equation to figure out a deseasonalized sales prediction for the first quarter of 2006. So these quarters that I had here, this was x equals 1, x equals 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what is x going to be in the first quarter of 2006? It's the next one along here, 2006 quarter 1 would be 13. So for x equals 13, I'm going to put that into this equation. I have y equals 0.78 times 13 plus 67.68, which gives me 77.82. So rounding that up to the next whole number, I'm going to call that 78. The original question actually stated that these figures were in thousands of dollars, thousands of sales. So the answer here will be $78,000 worth of sales for the first quarter of 2006. Say you are now asked, using this deseasonalized sales prediction, estimate the actual sales during the first quarter of 2006. So the difference here is one of these has been deseasonalized. It's had that seasonal index number applied to it to smooth it out. We want to know what the actual sales might be, so going back a step. So our deseasonalized sales prediction was 77.82. Now, to go back towards actual sales, we're going to need those seasonal index numbers. Remember, these were our actual data figures in this table, and these were the seasonal index numbers we worked out. Now, we're talking about the first quarter of 2006, which is this quarter here. So the seasonal index number that we're going to play around with is this one. And remember that formula, deseasonalized value equals the actual divided by the seasonal index? We can use that to go back the other way. If I want to know what the actual is, I want to get actual by itself on one side of the equals. I'm just going to get rid of this seasonal index by timesing it over there. I'll have deseasonalized times the seasonal index will give me the actual figure. So the deseasonalized figure was 77.82 times the seasonal index for that quarter, which was 1.021, will give me my actual figure. 77.82 times 1.021 gives me 79.45. So if I'm going to round that up to the nearest whole number, to the nearest 1,000, the actual sales during the first quarter of 2006 will be 79,000. And this is how seasonal index questions might look on an exam. This question is from the 2006 Exam 1. And questions 11, 12 and 13 all related to the following seasonal index table. The table shows the seasonal indices for the monthly unemployment numbers for workers in a regional town. The seasonal index for October is missing from the table. The value of the missing seasonal index is. Now remember I said the seasonal index numbers must add up to how many time periods there are. Because this is monthly, there are 12 all up. So these numbers along here, 1.3 plus 1.21 plus 1 plus 0.95, these numbers must add up to 12. So to figure out what October is, we just say 12 minus all of these numbers. So put that into your calculator and you'll get 0.98, which makes the answer D. The next question said the actual number of unemployed in the regional town in September is 330. So here's September, we're talking about this time period here. The deseasonalized number of unemployed in September is closest to. Okay, so remember our formula deseasonalized equals the actual divided by the seasonal index. So here we know that the actual is 330. And we know the seasonal index for September is 0.94. So whack that into your calculator and you'll get 351. So the answer is C. The third and final question that related to this seasonal index table said, a trend line that can be used to forecast the deseasonalized number of unemployed workers in the regional town for the first 9 months of the year is given by deseasonalized number equals 373.3 minus 3.38 times the month number, where month 1 is January, month 2 is February, and so on. The actual number of unemployed for June is predicted to be closest to. Okay, so here we have a formula which is giving us the deseasonalized number. And from that, we're going to work out what the actual number is. So the first step is to use this formula to work out the deseasonalized number, and then we'll convert it to an actual. So if we're trying to find the unemployed for June, what month number is that? Now January was 1, February was 2, March was 3, April was 4, May was 5, makes June number 6. So the month number that we're going to plug in here is 6. So we have equals 373.3 minus 3.38 times 6, and we get 353.02. So that is my deseasonalized figure for June. Now to convert a deseasonalized to an actual, which I'm actually trying to find, I use the formula deseasonalized equals the actual divided by the seasonal index. Now I'm trying to find the actual, so I need to get the actual by itself with actual equals something. So if I'm trying to get the actual by itself, on one side of the equals, I'm going to times this seasonal index away. Because the operation here, it's been divided, I just do the opposite. I times it over here and I get deseasonalized times the seasonal index equals the actual. So using these figures, I'll have 353.02 times the seasonal index, which for June was 0.86, and that will give me the actual, which is 303.5972. My answers have been rounded to whole numbers here, so what's 303.5972 rounded to a whole number? 304. So the answer is A.
Method of simple average. Method of simple average is faulted on account of the fact that all past periods are given same importance, whereas it is justifiable to accord higher importance to recent past periods. Moving average method takes a fixed number of periods, and after the elapse of each period, data for the oldest time period is discarded and the most recent past period is included. Whatever the period selected, it must be kept constant. It may be 3, 4 or 20 periods. By once it decided, we must continue with same number of periods. Simple average is equal to sum of demands of chosen periods divided by number of chosen periods. Summary. Forecasting demand helps a firm to arrange for the supplies of the necessary inputs without any wastage of materials and time, and also helps a firm to diversify its output to stabilize its income over time. The concept of demand forecasting is more relevant to the long run than the short run. Qualitative forecasting consists of gathering opinions from a variety of people, then applying their own judgment. Method of simple average is faulted on account of the fact that all past periods are given same importance, whereas it is justifiable to accord higher importance to recent past periods. Moving average method takes a fixed number of periods, and after the elapse of each period, data for the oldest time period is discarded and the most recent past period is included.